Hi there, pre-calc students. We're going to continue on this continuity lesson here, 3B, with some more slides and primarily some more examples. Just wanted to review these different types of discontinuities. Again, we've learned about these in the earlier part of the course, but just list what they were and just show you some visual examples of those. First of all, we have a point discontinuity. Sometimes in fact, this textbook that we use for these problems would refer to it as a removable one. Typically what this would be is you'll have something that's graphed and there'll be that one little hole in there and then it goes on from there. So, for all practical purposes on your graphing calculator it looks like a straight line, but if you examine your table you'll see that there's that little hole or that one place where it's undefined. Secondly, we have a jump discontinuity. I think you're kind of aware what that is. And we've seen some of these with absolute value connotations with them. So here's an example of what this might look like. Again, there's a clear break in the graph and actually a physical jump from one point to another. Then of course we have the infinite discontinuity. That almost always happens when there are vertical asymptotes and the graph will just start shooting way up or way down when it runs into those vertical asymptotes. Now the one that's a little bit different that we haven't really seen much before is called oscillating, and what this might be like is the graph will continually bounce between positive and negative, and it might get a little bit bigger as you go along, or maybe not, but it just never really homes into any one particular y value. So that one's fairly rare, but it is one that's listed and we might encounter at some point. So just to be aware of those, we like to classify those different types of continuity when we see them as well. Now a couple other miscellaneous things to mention here. Continuous function is continuous at every point of its domain. So for instance, if we have this particular function right here, which is y equals 1 over x, and I've showed the graph of that. Obviously something goofy is going on at 0. There is one of those infinite discontinuities there. However, at every point of its domain, really x equals 0 is not part of the domain. So I'm going to write that in there. X equals 0 is not a part of this domain. So then if we go very strictly by this definition, which mathematicians tend to do, we would say that this is a continuous function. It is just not continuous at the point x equals 0. So because x equals 0 is not a part of the domain for this function, we can conclude that this is indeed a continuous function. So kind of screwy definition here. You have to watch out for it a little bit. But that's the deal with this. Alright, here's another thing that we had studied about before, composite functions. That's like the f of g of x, g of f of x. So the idea here is that if f is continuous, f is a particular function. If f is continuous at c and g is continuous at the f of c, then the composite g of f is continuous at c. So for instance, if I looked at a particular function like this, y equals the sine of x squared, and one would wonder whether that's a continuous function or not. Again, you could look at this on your calculator graphing wise perhaps, but if I look at the two parts of this function, one of them which would be y equals the sine of x, and the other which would be y equals x squared, and really that is a composite. It'd be like the f of g of x or g of f of x to get to this original function we were given. So the idea is because the sine of x is continuous, because x squared is continuous, when I do the composite of both those things, it's also considered to be continuous. So this combo platter of composites right here is considered to be a continuous function. One other quick example of this, let's say I had y equals the absolute value of the cosine of x. Again, if we look at the individual pieces of that, one of them was y equals the cosine of x, one equals y equals the absolute value of x. We see that these are both continuous functions. Cosine of x is continuous, absolute value of x is continuous. That's just our v-shaped graph. So when we put those together with a composite, the result is also continuous. All right, here's another good example that I'm sure we will see. I didn't write the function in here. I'm going to now, since it was a little bit tricky to do. So f of x equals 2x plus 3 when x is less than or equal to 2, and ax plus 1 when x is greater than 2. What we'd like to do is see if we could find some value for a here so that when I graph this all out, it will become a continuous function. So we'll make use of the graph and also some algebraic ideas in this particular case. So first thing I think I would do is figure out, well, at x equals 2, what's the value of my top function there? So then I'm going to have 2 times 2 plus 3, and that will actually equal 4 plus 3 is 7. 7. So in other words, the ordered pair 2, 7 is going to be kind of crucial here. I'm going to try to mark that here a little bit if I can. That was a little bit off. So when x is less than 2, this function is going to be graphed on that particular point, and I notice that it does have a slope of 2, so that means I can go down 2 and back 1, so roughly like that. That's what the function looks like, the left part of it anyway. Now the right part, I'm trying to figure out this a value, remember, so ax plus 1 when x is greater than 2. Now the idea is if I want this to be continuous, it would be nice if that other function just picked up right in here where we left off and then went and did its own thing. But it'd be nice to know what that value was or would have to be when x actually equals 2. So probably the way to do that, I think, would be just to take this bottom one, the ax plus 1, but I am going to put in 2 in place of x. And I want that actually to equal 7. And why 7? Well, that's what the current y value is up there. If this is going to be continuous, they certainly have to meet up. So in solving this little equation, I get 2a plus 1 equals 7. I subtract 1 from each side, so 2a is 6, and therefore a must be 3. So if a is 3, and we could sort of verify this a little bit, I'll try to change colors here. If a is 3, then we will get y equals 3x plus 1. And if I just start graphing that a little bit, y-intercept of 1 and the slope of 3. So I'm going to go up 3 and over 1, up 3 and over 1, up 3 and over 1, and sure enough it does land right on this, and then just keeps going up a little bit higher like that in kind of a steeper graph. So, and because of my signages here, because top one is less than or equal to, bottom one is greater than, but because they both intersect here, there's no hole in the graph, and therefore this is a continuous function. Thanks for hanging in here, gang. Just one more problem to go over. Again, a similar to what we just talked about with just a little different wording. So now we're looking for a formula for the extended function that is continuous at x equals 1. And the problem gives us this particular problem here. So the extended function, meaning that they don't want to have any domains, issues or anything like that. And so let's take a look at what we might do here. So here's my function, x cubed minus 1 over x squared minus 1. I graphed it, kind of a strange looking graph, although it does look like it might have one of these slant asymptotes, if you remember when we picked those up. Now, at x equals 1, you can see that there's an error because of the x squared minus 1 in the denominator. Putting a 1 in there would make this go bad. But let's see if we can figure out what this would have to be. Now, this is a little bit math leaguey, I think, but don't be too intimidated. There is a way to factor expressions like this, which is something cubed minus 1. And the way to actually factor that out, I'm just going to write this out. It's going to be x minus 1 times x squared plus x plus 1. Meanwhile, we have my usual denominator there. That hasn't changed. I'm going to factor that out a little bit. That's x minus 1 times x plus 1. That's how to factor a difference of squares like that. Now, notice what I can do. Now, since I have some factored forms here, I can do some canceling of these things. So I can cancel out those x minus 1s. My resulting function that's left is, maybe if I can write it down here, x squared plus x plus 1, all of that over x plus 1. That's called the extended function because notice at x equals 1, this thing will be defined. This will not go bad when x equals 1. And we could figure out specifically what the value would be, but the idea is that this is an extended function right here. I can write it like that. And this can help me figure out some discontinuous points on some of the problems I'm working on here. All right, thanks for hanging in here on this. This is kind of tough sledding, as you figured out, but good work, and we'll see you guys in class tomorrow.